All right, let's take a look at this. So what is the activity of 13 grams of cobalt-60 if it's got a half-life of 5.2708 years, right? Um, what we're going to do here, the strategy is we're going to figure out the decay probability. It's going to be something per second. It has to be per second, right? Okay, that'll be our first step, right? Our second step is we've got to figure out how many atoms there are, right? And then our last step is that the activity is going to be the decay probability times the number of atoms. It's going to be a big number, right? Okay, so let's do this first. Let's figure out the decay probability in seconds, right? So that's going to be ln2 over the half-life, right? Okay, but the half-life has to be in seconds, and here it is in years, so that'll take a little doing, right? So ln2 over, and then it's 5.2708. That's years. All right, and then we're going to multiply by 365, and I think it's about a quarter, right? 0.24. I don't know. We'll say it's a little less than a quarter. I don't even know. Okay, and that is days per year. All right, multiply by 24 hours per day. Those will cancel out. Years cancels out. And then multiply by, 30. Okay, there we go. 3,600. The pen got stuck in constrained mode. Okay, and this is seconds per hour, right? So now finally we've got seconds, right? All right, so natural log of 2 divided by parentheses 5.2708 times 365.24 times 24 times 3,600. All right, and I'm getting that is 4.1673 times 10 to the minus ninth per second, right? That's a vanishingly small probability, 4 parts in a billion that it's going to decay, right? All right. So then our next thing is to figure out the number of atoms. So that's going to be Avogadro's number times the number of moles, right? And so Avogadro's number is 6.02 times 10 to the 23rd atoms per mole, right? And then we're going to multiply that by the moles we have. So it's 13 grams divided by moles per gram is 59.934, right? Okay, so 6.02 times 10 to the 23rd times 13 divided by 59.934. This is a whopping 1.305769 times 10 to the 23rd atoms. All right, now we're ready. Are you guys ready? This is the exciting moment. Our activity is just going to be the decay probability times the number of nuclei. So it's going to be 4.1673 times 10 to the minus ninth, and that's seconds to the minus 1. That's the probability per atom, right? And boy, you got a lot of atoms at 1.305769 times 10 to the 23rd atoms, right? That's going to be a lot of decays. Okay, so that times that. And I get that the answer is 5.44 times 10 to the 14th counts per second. Now that's just insane, right? So the question is, how could you possibly detect that much activity, right? No detector can do this, right? Okay. So the answer is that you put the substance here, and then we know that it's spreading out, and it's a uniform displacement. So we move ourselves back at some distance. We put a detector there. We know the efficiency of the detector. We know how much of the solid angle we've subtended by the detector's active parts, right? And we do maths. Okay. Okay. All right.